name is Anne Green and I'm from the University of Nottingham in the UK, and I'm going to be talking to you about primordial black holes as a candidate for being some of the dark matter. As I'll tell you later on this morning, it looks like they can't be all of the dark matter. So it's something of a scientific random walk that sort of led me to being here talking about this topic. I did my PhD many years ago on inflation, and one of the things I worked on there was primordial black holes as a constraint on models of inflation. About that time, the Macho microlensing collaboration had evidence for dark matter in the form of solar mass compact objects. So this led me to working on microlensing, and then that led me on to working on WIMP dark matter, because this was about the time that the DAMA direct detection collaboration first announced their annual modulation signal. And so I've then spent most of the last 20 years working on WIMP direct detection, spending a little bit of my time still working on early universe cosmology, inflation, and primordial black holes. However, in the last couple of years, thanks in part to the LIGO observation of the mergers of really massive black hole binaries, there's been a huge resurgence of interest in primordial black holes. And so hence this has led me back to what I was working on nearly 20 years ago, this topic of primordial black holes and whether they can be part of the dark matter. So the layout, I'm going to start with a very brief overview of the motivation for primordial black holes as a dark matter candidate. This first lecture is mainly going to be focused on the formation of primordial black holes. There are various mechanisms that they can form by. You basically have to get a lot of material in a very small place to form a black hole. And the main way of doing this is density perturbations produced presumably by a period of inflation in the early universe, and I'll explain in some detail what inflation is. And if these perturbations are very large, they can collapse and form black holes. And so this is the main mechanism for forming primordial black holes, and it's the one I'll focus on, but I'll also mention briefly other ways of doing it. And then finally, to wrap up this first lecture, I'm going to talk about the mass function of the black holes, because this is something that turns out to be absolutely crucial when you then start studying constraints on their abundance. The second lecture, that's going to then be a look at the long list of constraints on the abundance of primordial black holes there are from various observations, and then finally wrapping up by looking at how you apply those constraints to extended mass functions. So, as with any topic, there's a limit to what I can say in 2 hours. This is also an area in which there's been a really fast rate of publications over the last couple of years, and it's been hard for me to sort of keep up with everything, so there may be things I miss. If you're interested in further information on these topics, well, I'm going to be scattering references throughout, but another good place to look is a very recent review paper by these guys from last month. They cover all of these topics in a lot more detail, and they also discuss in much more detail than I will the possibility of primordial black hole binary mergers being the source of the LIGO gravitational wave events. So, first up, the motivation. As you all already know, there's an abundance of cosmological and astronomical evidence that a large fraction of the universe is in the form of cold, non-baryonic dark matter. So historically, a lot of the work on dark matter has focused on WIMPs, weakly interacting massive particles, as the dark matter. But as you've already heard yesterday, over the last, say, 5 years, there's been a broadening of the range of possibilities people are considering, both in the terms of WIMPs, considering a wider range of masses and interactions, and also looking at other dark matter candidates. For instance, axions were mentioned in the discussion session yesterday. Primordial black holes are another possibility. And one of the key things is they form in the early universe before nucleosynthesis, and therefore they're non-baryonic, which is one of the key requirements for a good dark matter candidate. Famously, primordial black holes evaporate by emitting Hawking radiation, so very light primordial black holes will have already evaporated. However, their lifetime is longer than the age of the universe if their mass is greater than 10 to the 15 grams. So primordial black holes that are more massive than 10 to the 15 grams are effectively stable, which is another requirement for our dark matter candidate. The big difference from other dark matter candidates, for instance WIMPs, axions, sterile neutrinos, etc., is that primordial black holes aren't a new particle. That somehow sometimes led people, myself included, to say that that means that they don't require new physics beyond the standard model. However, that's probably not quite strictly true. As we'll see later on, to make them, you need to do non-standard things in the early universe, and that probably, their formation at least, requires beyond the standard model physics probably. So that's the motivation for sort of dark matter, primordial black holes as a dark matter candidate in general. The recent interest has really been spurred by a couple of years ago, discovery by LIGO of gravitational waves from mergers of massive black holes, multiple tens of solar masses. Now, I'm not at all an expert on astrophysical black holes. My understanding is that such massive black holes could have been formed by astrophysical processes potentially, but no one was actually expecting to see quite as many of them as has been seen. So this, I think, so people have been suggesting that these objects could be primordial black holes. I'm, I guess, naturally scientifically quite conservative, and if I had to bet, I'd bet on these things being astrophysical black holes. But it's one of those things where, you know, the work needs to be done to work this out and work out whether these black holes are astrophysical or primordial. But anyway, put all of this together, it leads to the question, could primordial black holes be some or all of the cold dark matter, and potentially also the source of these gravitational wave events?
Before you go on,
yeah.
Why does it matter that primordial black holes are non-baryonic? I would think it's completely irrelevant if they're baryonic or not.
Well, because we know the dark matter has to be non-baryonic, that nucleosynthesis, CMB, they all point to the fact that only a small fraction of the dark matter is in the form of baryons. The majority of the dark matter has to be non-baryonic.
So how can you tell that black hole is non-baryonic?
Well, because they formed before nucleosynthesis, so before the baryons were formed. So they're just radiation collapsing.
Okay.
Okay, it's probably a good point for getting straight though, because you know it's
probably something that we should discuss afterwards.
I mean, okay, but
yeah. It's okay, don't worry.
So moving on to the formation of black holes. So this goes back to, well, Hawking gets most of the credit, but as always, there were some Russians doing similar stuff just before, Zeldovich and Novikov. And so what happens is if you have a very large density perturbation, then during radiation domination, shortly after it enters the horizon, i.e. becomes smaller than the observable universe, and that's something I'll come back to later on in more detail, then gravity can overcome pressure and the fluctuation collapses to form a black hole. And the criteria for this to happen is that, so initially the region is expanding, it comes to a maximum and then collapses, and at that maximum, it must be larger than the Jeans length. Below the Jeans length, pressure is going to overcome gravity and stop it collapsing to a black hole. So it's basically the length scale below which pressure affects things. You'll probably hear more of that later this afternoon. It's something which comes up a lot in structure formation. So a very simple analysis, which goes back to the 1970s by Bernard Carr. There's a more recent paper that refines this, but sort of comes to a similar answer. So the key quantity is the density contrast. Density minus the average density divided by the average density. And the threshold of this for black hole formation, it has to be greater than some critical value. And very roughly, that is equal to W, which is the equation of state parameter, P equals W rho. And for radiation domination, which we're focusing here, W is a third. So just to emphasize, these are really big density fluctuations. These are the values at horizon entry. And as I'll sort of emphasize later on the CMB and large-scale structure scales, the size of the fluctuations at horizon entry is 10 to the minus 5. So these are very definitely much larger fluctuations. If a fluctuation satisfies this requirement, then it collapses and forms a black hole, and the mass of the black hole is roughly equal to the horizon mass, i.e. all of the mass within the observable universe at that time collapses to form a black hole. And the horizon mass, you can write, it's about in this form here, so I've normalised here to 10 to the 15 grams, i.e. the size of things which would be evaporating today relative to time. So very small things would form at really, really very early times, deep within the radiation-dominated period. So a quantity that gets used a lot is the initial PBH mass fraction. For some reason it gets called beta, and it's the fraction of the universe which is in regions which are dense enough to form primordial black holes. So you take the probability distribution of the size of your fluctuations and you integrate it above the critical value. So anything above that critical value can collapse to form a black hole. Assuming that this probability distribution is Gaussian, and that's a big assumption that I'll come back to later on, what you end up with is the complementary error function from integrating over the tail of a Gaussian. So this figure sort of sketches this out. So we've got a Gaussian distribution. There's a quantity sigma, which is called the mass variance, and it's essentially the typical size of the fluctuations, i.e. the width of this distribution. And then we've got our critical value of order a third, and then anything out in this tail that's bigger than that can collapse to form black holes. As we'll see later on, actually the initial fraction of black holes has to be very small. So this is actually a very exaggerated diagram. What you'd actually have is a much smaller width and then a tiny fraction of the distribution out here in the tail above the critical value. If this mass variance was independent of mass, i.e. the fluctuations all had the same size on all scales, the primordial black holes would have a power law mass function, and that's what Bernard Carr found in his first paper on this back in the 1970s. But typically what you get is a particular scale where the mass variance is largest, and that's where you'll get the majority of the black holes forming. But I'll come back to the mass function of the black holes at the end of this lecture. So now let's talk about the abundance of primordial black holes. So the key thing is once they've formed, they're matter. So the density in black holes dilutes as the scale factor A to the minus 3. However, radiation dilutes as A to the minus 4. Therefore, during radiation domination, the fraction of energy in primordial black holes, i.e. the density of the black holes divided by the density of radiation, grows proportional to the scale factor. So you can have a very small fraction in black holes initially, and during radiation domination, it grows. And with a few lines of maths, you can end up with this relationship between the initial mass fraction beta, which we just met, which comes from integrating over the probability distribution, and the fraction of dark matter in the form of primordial black holes today, which gets called F. And so what you see is it depends on the mass of the black holes. The horizon mass increases with time, so little black holes form early and have the longer amount of time to grow as a fraction of the density. But what you see here is that to get F of order unity, i.e. the black holes to be the dark matter, this beta has to be absolutely tiny because the fraction of the universe in black holes grows with time. Now, as I've already mentioned, on CMB scales, we can measure the amplitude of the primordial perturbations, and it's of order 10 to the minus 5, i.e. very small. And what you can then do is insert that 10 to the minus 5 into this expression for the mass fraction of black holes, putting in delta C of order a third. And what you get out is that in this case, we've got an exponential of minus 10 to the 5 squared. So what that's telling you is if the primordial perturbations have this value on all scales, the amount of black holes you make is absolutely negligible, practically zero. So to get an interesting number of black holes, you need this mass variance, the typical size of the fluctuations, to be significantly larger on small scales than on cosmological scales. And so if you sort of say that you want F to be roughly equal to 1, you can work out the corresponding beta you want. You can then go back to here and work out the corresponding sigma, and what you get is it has to be something of order 10 to the minus 2. So 3 orders of magnitude bigger. And a large fraction of my first lecture is going to be devoted to talking about ways in which you can make that happen, ways in which you can make the primordial perturbations large on small scales. So just to emphasize that, this is a plot of constraints on the primordial power spectrum. The axes here, for anybody who knows about cosmology, are the power spectrum of the density perturbations and the power spectrum of the curvature perturbation. But essentially, these are both equal to this quantity sigma, the mass variance squared. So that's the typical size of perturbations squared. And then we've got wave number k in inverse megaparsecs. So over here, small k, or large physical scales, we've got the scales probed by large-scale structure and the CMB. And what you see here is that we've got a very accurate measurement of the size of the perturbations, and they're very small. On this range here, there are constraints from something called ultra-compact mini-halos. These are very dense dark matter structures that can form fairly early. And if most of the dark matter is in the form of WIMPs, then you can get WIMP annihilation from these things, and there are then constraints from Fermi and the CMB, which say that on those scales, the size of the perturbations has to be smaller than this red line here, so somewhere in this region here. Although over the last few months, there's been some questioning of these calculations, so this red line is probably going to go up or down a bit when the details are thrashed out. But this important thing for the context of this talk is this black line here. This is the 10 to the minus 2 that I've just told you that is needed to form an interesting number of primordial black holes. So what I told you initially was a very simple scenario for the formation of the black holes. There are some deviations from this simple scenario that are probably important. So the first up was this assumption that the primordial perturbations are exactly Gaussian. That may not be the case, and in particular, since the primordial black holes are forming from the rare fluctuations out of the tail of the distribution, changes in the shape of the tail of the distribution could have a really significant effect on the number of black holes you form, i.e. the fraction of the distribution that's above the threshold. And this is something that many people have looked at going back to the 1990s, including your lecturer of this afternoon has actually written a paper on primordial black holes and non-Gaussianity. So it turns out to be a very difficult problem. You can do concrete calculations for concrete models for producing the black holes, but doing something more generally is difficult. And in particular, there's been what I think is a really nice paper very recently by these guys, where they use a path integral formalism for deriving exact expressions. But the problem is the exact expressions you end up with are extremely difficult to then evaluate. So I think the bottom line here is that non-Gaussianity is probably, depending on the model, going to have an important effect on the number of black holes you produce, but it's very difficult to do the calculations. The next thing is something called critical collapse. So this is a phenomena that shows up in the formation of black holes, not astrophysical black holes, but sort of general relativistic black holes more generally. And it says that the size of the mass of the black hole you form depends on the size of the fluctuation it forms from. And in particular, it does so in this way here. So mh is the horizon mass at the time the black hole is forming. K is a constant. And then we've got a power law here in terms of how big the fluctuation is relative to the critical density. So Our previous assumption before was just that the mass was roughly equal to the horizon mass, but instead we've actually got this power law dependence. And Niemeyer and Jadamczyk were the first people to sort of point this out as something that applied to primordial black holes. More recently, there's been a series of simulations by Musko, Miller and Polnareff, and they set up appropriate initial conditions for primordial black hole formation. And here are their results in terms of the masses of the black holes they form relative to the horizon mass, and then also the size of the fluctuations above the critical density. And they really do see that you do get this power law in the masses over a huge range of densities. And in particular, they find the parameters that best fit this. And in particular, they find for this critical density, the threshold you need to be above to form a black hole, they find it to be 0.45. So the key point here is that even if all of the black holes form at the same time, i.e. a fixed value of the horizon mass, they won't all have the same mass. You're going to get a range of masses. And so we don't expect the primordial black hole mass function to be a delta function. It's going to have some spread. Third caveat, which is particularly relevant if you're interested in solar mass and tens of solar mass black holes, is the effect of phase transitions. So the calculation I showed you was for radiation domination, i.e. an equation of state parameter W equal to a third. At a phase transition, W can be reduced, and the net effect of that is it makes it easier to form black holes. And so it was pointed out quite some time ago by Carsten Jadamczyk that the horizon mass at the QCD phase transition is of order a solar mass. So this reduction in the equation of state parameter there, you could expect to produce more black holes with of order a solar mass. Now, our understanding of the QCD phase transition has evolved with time. People once thought it could be a first order phase transition, and this would have then been a very significant effect. It's now known not to be, but nonetheless it's still significant, and there's been a recent paper by Chris Burns and collaborators where they use the most accurate studies of the QCD phase transition and work out how the number of black holes is affected. And so these are their results for the present day fraction of black holes as a function of mass relative to a solar mass. And so this is what you get, the black line, without taking into account QCD phase transition. If you do take it into account, you get an enhancement here around a solar mass and also a sort of bump here out at tens of solar masses. However, this is sort of an enhancement by, say, an order of magnitude or so. On its own, it's not enough to produce lots of black holes from a scale invariant spectrum. You still need to be doing something to amplify the primordial perturbations in the first place. So, with the standard scenario and some caveats wrapped up, the next question is, well, we need the perturbations to be big on small scales to produce primordial black holes. How can we do that? And it's something that shows up in models of inflation. So just before I sort of get started, how many of you know what inflation is? Stick your hand up. Okay. How many of you have studied inflation in some detail? Okay, well, I will try and give a sort of fairly decent introduction to inflation. This is probably something it's useful to know about in general. So even if you're not particularly interested in the primordial black holes, a bit of background about inflation is no bad thing. So in simplest terms, inflation is a period of accelerated expansion in the early universe, so A double dot greater than 0. And it was proposed back in the 1980s because of various problems with the Big Bang. So first up is the flatness problem. If the universe is exactly flat, it stays exactly flat for all time. But if there's a small deviation for flatness, then it evolves away from flatness even more as the universe expands. And what we know today from the cosmic microwave background is the density today is very close to the critical density for which the universe is flat. So that suggests fine-tuning of the initial conditions to be extremely close to flat at early times. The next problem is the horizon problem. The cosmic microwave background has the same temperature and anisotropy distribution in all directions. However, if you do a calculation of what the size of regions that could have been in causal contact at the time the CMB radiation was released, those regions are about a degree across on the sky. So these regions that have never been in causal contact end up having the same CMB. And then finally, the sort of motivation initially for inflation was something called the monopole problem. And that was when you have grand unified theories, when symmetry breaks, you get massive relics such as monopoles formed. And like the black holes, the fraction of the universe they make up increases with time. And so they would have come to dominate the density of the universe, and it would just look completely different till it actually does. So inflation solves these problems. So the accelerated expansion drives the initial density to be extremely close to the critical density. So even though it evolves away after inflation, it can still be very close to the critical density today. The horizon problem is solved because you get a very small region which could initially have been in causal contact and in thermal equilibrium. It then gets blown up to be bigger than the observable universe today. And then finally, any troublesome relics, they'd have simply been diluted away by the expansion. So the initial motivation for inflation was solving these problems, but at around the same time as it was proposed, it was realised that inflation could also do something else that we need. And that is provide a mechanism for generating the primordial perturbations from which the structures we observe in the universe form. So the idea here is that inflation is driven by something called a scalar field. Quantum fluctuations in that scalar field lead to curvature perturbations that then source the density and temperature perturbations that we see in the universe. And those perturbations are close to scale invariant, i.e. have the same amplitude on all scales, and they're consistent, at least, with what we measure for the temperature anisotropies in the cosmic microwave background radiation. So the question is, what drives inflation, i.e. what do we need to get the scale factor A double dot to be greater than 0? So the fluid equation tells us how the density of any thing in the universe evolves with time due to the expansion of the universe. And it allows you to derive what's called the acceleration equation, which relates the acceleration to the density and the pressure. And what you see is the requirement that A double dot is greater than 0 requires something with pressure less than minus a third rho. So in other words, you need something with negative pressure. And the potential thing in particle physics that can give you that negative pressure is a scalar field. So this is something, a spin 0 particle, and sorts of things that are required for spontaneous symmetry breaking. For instance, the Higgs is a scalar field. And the key thing is that you get these expressions for the energy density is the kinetic energy plus its potential. The pressure is essentially the kinetic energy minus the potential. And what you see is, if the potential dominates over the kinetic energy, you end up with an energy density that's roughly equal to minus the pressure. So in other words, a scalar field has this property of having negative pressure that we need to drive accelerated expansion. So a very quick overview of the dynamics of scalar fields. So the key equation in cosmology is the Friedmann equation, which is h squared equals 8 pi g divided by 3 times rho. So I've substituted in here rho for our scalar field. And the fluid equation for a scalar field takes this form here. So essentially, this is very much like the dynamics of a ball rolling down a hill. And a key thing in inflation is something called the slow roll approximation. It essentially says that the field evolves very slowly down its potential. And you get these things, epsilon and eta, called the slow roll parameters. Epsilon is defined in terms of the slope of the potential, and eta in terms of the curvature of the potential. And if these slow roll parameters are small, i.e. the slope and curvature are small, you end up with the simple form here for the Friedmann equation and the fluid equation. And you can show that the first slow roll parameter, epsilon being less than 1, is sort of equivalent to the requirement for accelerated expansion. So what happens is you've got this scalar field is slowly rolling down its potential, and when the potential becomes too steep, inflation stops, the field oscillates around the minimum of the potential, and it decays into standard model particles, reheating the universe. So the condition for accelerated expansion, A double dot less than 0, can be rewritten in terms of something called the co-moving Hubble radius. And that's basically the size of the observable universe. H to the minus 1 gives us a scale, and we divide by A to get into what's called co-moving coordinates, coordinates that expand with the universe. And so A double dot being greater than 0 is equivalent to this co-moving Hubble radius decreasing with time. So in this plot here, I've plotted the variation of the co-moving Hubble radius with time. During inflation, it decreases very, very rapidly. Then afterwards, during radiation and matter domination, it increases again more slowly. And a key thing is when a scale enters and exits the horizon. So we specify in cosmology scales in terms of the co-moving wave number k, and so it's equal to the horizon size when k equals AH. So this first scale I've drawn here, K1, and here it's plotted as its inverse, so we can compare it to the co-moving Hubble radius. It's initially inside the horizon, so smaller than the observable universe. So at some point during inflation, it goes outside the horizon, and then it comes back in at relatively late times. So this coming back in at relatively late times is a scale which corresponds to the scales that form large-scale structure, galaxies, galaxy clusters, the CMB. Down here, we've got a smaller scale. It exits the horizon close to the end of inflation, spends a little bit of time outside, and then comes back in again during radiation domination. And it's these sorts of scales on which we can potentially form primordial black holes. So just to make that more concrete, the CMB in large-scale structure probe co-moving wave numbers between 1 and 10 to the minus 3 inverse megaparsecs. Primordial black holes can potentially form on a range of much, much smaller scales. And we can write down a relationship between the horizon mass and temperature, which is probably a bit more intuitive than the one I previously showed you with time. And so when the temperature is about 10 to the 7 GeV, we've got a horizon mass of about 10 to the 18 grams. And so the reheat temperature at the end of inflation, i.e. the sort of temperature from which the hot Big Bang starts, that sets the smallest scale of black holes you can form. So coming back to the amplitude of the fluctuations, so in this slow roll approximation I've talked about where the field evolves very slowly down its potential, the amplitude of the fluctuation squared is proportional to the potential cubed divided by its derivative squared. And you end up with it depending on wave number k to the power of ns minus 1, where ns is the spectral index, and the spectral index can be written in terms of these slow roll parameters epsilon and eta, and because during slow roll they have to be small, these are then giving you small deviations of the spectral index from 1. And a spectral index of 1 would correspond to this scale invariant spectrum I've told you about, where the fluctuations are the same size on all scales. So on large scales, because the CMB and large scale structure allow us to measure these things, so on a scale of 0.002 inverse megaparsecs, the amplitude, as I've mentioned before, is about 10 to the minus 5, and the spectral index is a little bit less than 1, 0.97. One thing I'll just mention as an aside, because it's a mistake people often make when doing primordial black hole calculations, is that when you're dealing with large-scale structure, it's common to take the power spectrum, or equivalently the mass variance squared, and expand it as a power law. Take its value on some pivot wave number, and then you've got the next term from the scale dependence, and then another term from the running. And that's fine if you're only interested in a relatively small range of scales. So it's fine when people do it on for the CMB and large-scale structure. But with primordial black holes, we're interested in a much, much larger range of scales. You can't do it. So practically, this is an expansion in log k divided by this particular wave number k0. And if you take k to be many, many orders of magnitude different from k0, an expansion just simply isn't valid. So before I get on to specific inflation models, has anybody got any quick questions about inflation in general? Yeah.
Can you just repeat what you said on the last slide about exactly what sets the scale for the mass of the black holes today?
So the question was, can I repeat what I said about what sets the scale for the black holes? So at the moment, I'm just saying, if they form on a particular scale, they'll have mass equal to the horizon mass. And what I've got here is a relationship between horizon mass and temperature. I think I'm going to answer your question in the succeeding.
Like how you choose the scale?
So yeah, I will address that question in the coming slides. Anything else? Yeah.
Can you just say what you said again about this scalar sort of then turning toward standard model particles?
Okay, so during inflation, you've basically got the entire energy density of the universe in this inflaton field. To have a hot Big Bang that works as we know it, you then need that field to decay into a bunch of particles and produces a hot radiation-dominated universe. That process is called reheating, and it's actually something that the details aren't very well understood. It basically depends on how the field that drives inflation is coupled to everything else. So it's something that, for the sorts of things I'm talking about, it probably doesn't matter a lot, and it also often gets hand-waved away, but it is actually a very active field of research working out how this process happens in detail.
Is there any hope for any experimental accumulation? Is that or?
So the awful thing with inflation is it's a fantastic idea, but one that turns out to be very, very hard to test. So I've sort of mentioned that what you see in the CMB is consistent with inflation in terms of the spectrum of the perturbations, but obviously something being consistent with something doesn't mean it's due to that. So this is sort of going off on a tangent, so I'll try and keep it brief. The way we really hope to test inflation, if we can, is something called a consistency relation. I've talked about inflation producing density perturbations. It also produced primordial gravitational waves, and there's a relationship between the amplitude of those things. So if we were to detect primordial gravitational waves and their amplitude matched what we expected, that would be the champagne bottle moment. And a few years ago, BICEP 2 announced the discovery of what they thought was primordial gravitational waves. Turned out not to be, it was dust, and therefore. So I think the problem is that inflation is this just elegant idea, but one which is very, very hard to test observationally.
So not from a particle physics?
The problem being the energies involved are so much higher than what you can probe at a collider. So in some ways that's exciting, because inflation is your mechanism for probing these high energies potentially. But it also means it's very difficult to make contact with experiments, so theorists can get a bit carried away. But it's probably best if I leave that now, and you can ask about it more later today, but it's, yeah, a bit tangential to where we're going. So anything else quickly on inflation in general? Right, so now coming on to models which might produce black holes. So what we want is large perturbations on small scales. So on CMB scales, we know the perturbations are small, and then we've got to grow them to be big on small scales to make black holes. And so it turns out that if you've got a model with a single field, to do this, you have to violate slow roll. And what that means is the expressions that I've shown you previously, for instance, that the amplitude of the perturbations is inversely proportional to the slope of the potential squared, aren't valid. And so there have been papers written where people have said you can produce large potentials by just having an inflection point on your potential. However, various people have sort of pointed out over the last year or so that these sort of models where you have your field rolling incredibly slowly along a flat patch actually don't do the job because slow roll is violated. So what can you do? Well, general idea, which again is something that people have looked at for many, many years, is insert a feature in the potential of your inflation model. And so recent work in the last few months has looked at the possibility of overshooting a local minimum. So the idea here is you've got a potential that looks something like that. CMB scales leave the horizon during this range of the potential here. You produce your scale, close to scale and variance spectrum that you need to be consistent with inflation. You then carry on evolving and you have this local minimum followed by a small little local maximum, and then the potential gets very steep and inflation ends. And so the idea is you fine-tune your potential so it just sort of slides over this bump, and doing that ends up producing your large perturbation. So here we go with the power spectrum or the mass variance. Very small on large scales is required, and then when you reach this little feature in the potential, the amplitude shoots up to this 10 to the minus 2 that you need to make black holes. You might be thinking this looks ridiculously fine-tuned. You're right. They sort of quantified how fine-tuned it was in terms of having a quintic potential with terms up to phi to the 5, and you have to tune the amplitude of the phi to the 5 term at the level of 10 to the minus 8.5 to do it. So the lesson here is you can make primordial black holes by exerting a feature in your potential, but it's incredibly fine-tuned. Another possibility is what's called double inflation. So this is where you have a phase of inflation, inflation stops, you then have a second period of inflation. And it turns out that perturbations on scales which leave the horizon close to the end of the first period of inflation get amplified. So again, here's your power spectrum, scale invariant and small on large scales, and then you can get this bump. Similar sort of thing happens if you have two periods of inflation and you produce your large-scale structure perturbations during the first period and your primordial black hole forming ones during the second period. This is potentially less fine-tuned than this, but it's still somewhat contrived. Yeah?
For all of these models, does the B-mode ratio R, is it below, like, because you're forming these really large perturbations on small scales, how does it affect the B-modes?
Okay, so the question is, how does this link in with B modes, as in the gravitational waves? Because obviously we've now got a limit on forming those. And that's something that people have to worry about, because you'd expect when you violate slow roll, you're getting into regimes where you have a large R. I think it ends up not being an issue here. However, there is an indirect constraint from gravitational waves, which I'll mention in a moment. So you're right that this is a potential issue, but possibly not in the way you might have first thought. So I'll come back to that one. So, okay, so that's having to do contrived things with single field models. You can also look at multi-field models. So a multi-field model of inflation that's sort of quite nice in that it's something that can sort of prop up in supersymmetric models is hybrid inflation. So in this case, you have two scalar fields with a potential that looks something like this. So initially your field slow rolls along this minimum here, and then you get to a point where that's no longer a global minimum. You've got symmetry breaking, you've got two minima here, and so your field then transitions into one of them, oscillates around the bottom, and inflation ends. And if you set your potential up so that this transition happens fairly slowly, the field sort of evolves away here quite slowly, and again, you can get a peak in your power spectrum. In this case, it's a very broad peak. So probably a bit less fine-tuned than the things I've already shown you, but nonetheless, you still have to tweak your parameters of your theory to get your potential to have such a shape that you get your power spectrum with a peak. I won't mention that. Another way of doing things, so all of these things I've mentioned, you've got a power spectrum and then you insert a peak at a particular scale. And so the question before of, sort of how do you choose? Well, you choose your parameters to put your peak where you want your peak to make black holes of a particular mass. So it's a sort of inserting features by hand. So this is slightly different. In this case, you have a power spectrum which increases monotonically with scale. And a case in which you can get that is something called running mass inflation, which was initially proposed by Yu and Stewart. And it has a nice simple potential, V0 plus half m squared phi squared, which is a sort of fairly common simple potential. But the difference here is this running mass, that the mass of the field depends on its value. So in that case, you can end up with a potential that looks like this, and a power spectrum that just increases monotonically with scale, being small as required on CMB and large-scale structure scales, and then getting big enough potentially to form black holes down here. And this is actually a case where not forming too many black holes actually constrains the parameter space of this model. So this is somewhat less fine-tuned, arguably. I won't talk about that either. I will very briefly mention other mechanisms for forming black holes. And so this is all sort of coming down to the early universe, radiation domination. How do you get a high density in a small region? So another way you could do it, which again, the early work was down to Stephen Hawking, is the collapse of cosmic string loops. So cosmic strings in general are one-dimensional topological defects that can form at symmetry breaking phase transitions. So the idea is you have a sort of Mexican hat potential, and when the symmetry breaks, you can end up in different minima around the circle at the bottom, and hence you get a one-dimensional defect. So you get these networks of cosmic strings, and they can intercommute, producing loops. These loops oscillate around, and there's a small probability that the loop gets into a configuration where all of its dimensions lie beneath the Schwarzschild radius, at which point you get a black hole forming. And the mass would be, again, be roughly equal to the horizon mass at the time that happens. And in this case, by studying the dynamics of these string networks, the probability of a loop doing this is independent of time, so you'd end up with the black holes having a very extended mass function. Another possibility, again related to phase transitions, is that first-order phase transitions occur via the nucleation of bubbles. So you get a field that tunnels from a false vacuum to the true vacuum, and so you get space-consistent regions, bubbles of the true vacuum, surrounded by the false vacuum where the field hasn't tunneled. When those bubbles expand and collide, you can get very high densities, and you can get primordial black holes forming. But the issue here is that you've got to fine-tune the rate at which the bubbles form relative to the Hubble expansion rate to make your bubbles expand enough, collide enough, but not too much. And another thing I just mentioned as a thing, because people have done work here on it recently, is another possibility is at the end of inflation, the inflaton scalar can fragment into things called either oscillons or cuballs, and then these things can then lead to the formation of primordial black holes. So I'm mentioning these things just to make it clear that the collapse of large inflationary density perturbations might be the most popular way of forming black holes, but it's not the only way. So finally, to wrap up this first lecture, I'm going to talk very briefly about the mass function of the black holes, and this will become apparent why this is important in the second lecture when we get to talking about constraints, observational and experimental constraints on the abundance of black holes. So if you have a primordial density perturbation power spectrum that's scale invariant, then for black holes forming during radiation domination, you end up with their mass function being a power law, m to the minus 5 halves. And this is something that Bernard Carr showed in some of the very first papers on primordial black holes. However, as I've already argued, if the power spectrum is completely scale invariant on all scales from the CMB right the way down, the number of primordial black holes you form is absolutely negligible. So the only time this would show up as being physically relevant would be if you had somehow a power spectrum that was scale invariant on large scales and also scale invariant on small scales with some sort of transition in between. So the bottom line is the inflation models we've been talking about that produce you black holes do not have this property and hence do not have this mass function. The one place it might show up, though, would be from the collapse of cosmic string loops. So this is something that's sometimes assumed, but actually is probably not a good assumption. It's certainly not one you should be making in general. So back when I was talking about the formation of black holes, I told you about critical collapse and this fact that we don't expect the mass of a black hole to be equal to the horizon mass at the time it forms. We actually expect it to depend on the size of the fluctuation as this power law. And the first papers sort of applying this to primordial black holes sort of pointed out what you then expect for your mass function. So assuming a Gaussian distribution for your perturbations, you end up with this functional form here, and what it looks like is this. So this is for all the black holes forming at a single horizon mass, and you get a spread of tens of % around that. So it's still a fairly short mass function, but it has some width. So then finally, the inflation models I was telling you about, where you can produce large primordial black hole forming fluctuations, they tend to not have a very narrow spike in the power spectrum. It has some width, and for instance in the hybrid inflation models it can be really quite wide. And so something I found sort of phenomenologically by just playing around, but some other people then came along and formalized it, is that actually in these cases you end up with an extended mass function that's basically a log normal distribution. So if you do want something practical to assume for what the mass function of your black holes is, a log normal distribution is a pretty good assumption. And so this plot is the mass function of the black holes for the running mass inflation model that I told you about, and an axion-like curvaton which I skipped through. And the black lines are for the actual models, the dotted and dashed lines are the log normal, and it's a pretty good practical fit. So a log normal mass function is a pretty good thing to assume for the mass function of your black holes. So to summarize this first lecture, there's been quite a lot of stuff, so let's sort of wind back. The most popular way of forming primordial black holes is in the early universe during radiation domination. If you've got a significantly large fluctuation, then it can collapse and form a black hole. The main issue with forming primordial black holes to be the dark matter is that you can only produce an interesting number of them if the amplitude of the fluctuations is 3 or 4 orders of magnitude larger on small scales than it is on big scales, the CMB and large scale structure. I've shown you various inflation models that can do this, for instance by putting a feature in the potential or having multiple fields. However, some degree of fine-tuning is required, and in case of the single field models with a feature, a huge amount of fine-tuning is required. So a key thing that will come up in the second lecture is that the primordial black hole mass function, we don't expect it to be a delta function. We don't expect them to all have the same mass due to this critical collapse physics where the size of the black hole depends on the size of the fluctuation from which it formed. And also we expect any feature in the primordial power spectrum to have finite width. Those things combine to give us a mass function that has some width. And one thing I'll mention here is that there are various aspects of calculating the abundance in primordial black holes and also their distribution, which aren't yet really well understood. I mentioned non-Gaussianity and the fact that we expect some deviations from Gaussianity in the large tail of the density distribution from which black holes form, but the calculations typically ignore that because including it is really, really difficult. And then I haven't mentioned these things, but I'll just flag them up here. One thing that, as far as I'm aware of, is not well understood is the clustering of primordial black holes. They form from these rare large peaks in the density field. We know from the mathematics of density fields that these rare peaks are going to be clustered, so you'd expect the primordial black holes to be clustered, but as far as I'm aware there's no really reliable calculation of working out quite how clustered they are and how that affects their distribution today. And then sort of linking into the motivation of primordial black holes being the origin of the LIGO, gravitational wave events, there are still some uncertainties in how mergers of the black holes affect their mass function. So there's been a lot of work over the last couple of years, in particular sort of constructing models and blah, but there's some difficult problems that actually need to be worked out properly to really see how viable primordial black holes as a dark matter candidate are. So yeah, that's it for this first lecture. Any more questions?
Since we have some time, could we talk about one possibility of forming primordial black holes that you haven't touched on, namely forming them in an early matter-dominated phase where you can have... Okay, very good.
So yeah, keep going.
Where you can, where you don't need a large density perturbation to come in, because the Jeans length, unlike in the radiation-dominated universe, is basically zero, and you can grow on perturbations on all scales. And then, depending on the length of your matter-dominated phase, you can make the primordial black holes almost as big as you want.
So you're absolutely right that, yeah, so once you go to matter-dominated universe, the criteria for primordial black hole formation are very different. So because there's no pressure, you don't have to have such large fluctuations to form black holes. It sounds like possibly you might know more about this than I do, but so here the requirement is that the fluctuations have to be significantly spherically symmetric, so they form a black hole rather than pancaking. And so in this case, and I think there is actually some... I don't know what I've just done. Yeah. There's actually some discussion about this formula. I think that power there is potentially wrong, the relationship between how much of the universe goes into black holes and this typical size of the fluctuations. But yeah, you're absolutely right. It's possible. The physics is somewhat different. I guess I now have to justify why I didn't include this in the bulk of the lecture. It's maybe because you're having to not fine-tune, but you're having to mess with the cosmological evolution. But the point being, I guess, that we don't know that the universe was radiation-dominated before nucleosynthesis, so hence it is something you can do.
The other great advantage of this is you don't need to mess with your inflationary potential, for example, or you don't need to insert features by hand. It is very much a, well, the physics that you have to do is you have to come up with or you have to have a model that gives you an early matter-dominated phase. But then from there on out, producing primordial black holes is much easier than in the radiation universe.
So what sort of values of the power spectrum do you need to do it?
Well, it depends on when your matter-dominated phase starts. And
yeah, because how long you've got to grow the...
Exactly, that. And the mass range depends. Well, the maximum mass is limited by how long the phase lasts, and the minimum mass is basically what the horizon mass is when it starts.
Yeah.
But you can do anything from 10 to the 8 grams to multiple solar masses.
And so, do you naturally produce quite a broad spectrum?
Yes, and even you don't even have to turn the spectral index up all that much, unless you want a very narrow mass function. Then you need a feature again.
Right.
But if you're fine with a very broad mass function, then your spectral index can be.
Although I'm nervous about spectral indices for the reason that I stated in one of my slides, that this parallel extrapolation isn't strictly valid.
So you said the G length drops, so these things are coupled to photons or something?
No, there's simply no pressure because you have dust. Basically, and then there's no pressure. Therefore, the Jeans length is 0.
Well, wouldn't this mess with the BAO if you're still saying that this is going to be a large fraction of the dark matter?
Can you repeat the question, because otherwise...
You should
So,
ask her.
okay, and then I'll repeat the question.
So, if you're going to be forming these primordial black holes during matter domination, and you're saying that they're a large fraction of the dark matter, wouldn't this mess with BAO?
So the question is, forming primordial black holes to be a large fraction of the dark matter during matter to domination, wouldn't that mess with BAO? I think the answer is that this is not BAO, baryon acoustical oscillations. So I think the answer is that this is not matter domination.
Many people do know what baryonic acoustic oscillations are. Many people would not. Am I wrong?
No, that's a good point. Yeah.
So maybe you can just.
So I think
mention
you're
that.
thinking matter domination at late times, whereas this is a new period of potential matter domination before nucleosynthesis. Because you can have fields come to dominate the universe and then decay, and then as long as you get back to radiation domination before nucleosynthesis, everything's fine. Do you want to add anything to that?
No, that's it.
So it has to be a different early period of matter domination. For example, if you have a very heavy particle, boson or whatever, that dominates the energy density and then it decays. And then, of course, if you get, again, a radiation domination, equilibrium erases all the previous history, except for these black holes that would be there. But it's
Another opportunity to
Here
pick
it
up.
is. Yeah, sorry.
Sorry, to pick up on this. Another opportunity is just to have the inflaton oscillating in its potential. Just have the reheating phase last long, and you get an early matter dominated phase.
And actually during reheating, so this is this decay of things at the end of inflation, you can actually amplify perturbations during that, which is something I probably should have mentioned but didn't.
Here
I
there's-
just caution that just being larger than the gene's mass is a necessary condition for collapse, but it's not really sufficient to figure out how you get a black hole. I mean, these early matter domination regimes where you have some heavy particle that's metastable, is long-lived. One issue there is that there's still a lot of radiation. So diffusive processes can diffuse energy in, for example, so it's a little tricky.
So you're absolutely right that the analytic calculations like this are disturbingly hand-wavy, and the Harada paper that's come back and looked at this recently has sort of acknowledged that the criteria you come out with depends on exactly even how you formulate your gene's mass. However, I think the thing that convinces me that this is not so unreasonable are these numerical simulations, and obviously then whether your results are reliable depend on whether your initial setup is reliable, but at least then you have an initial setup, you evolve it, and you see what happens.
I have a question. Can this early matter-dominated mechanism or periods, can they produce black holes that are producing bunches, let us say, that afterwards they can collapse into bigger black holes? This is the idea to try to get the black holes maybe as primordial black holes, the black holes observed by LIGO, right? That you form them clustered to start with, and therefore it's very easy for them to coalesce. Do they form this, or they can?
As it was said earlier, looking at more detailed analysis like clustering and merging, nobody has done, because this is so hand wavy already that you don't, or we haven't gotten into this yet, because we haven't actually figured out, we haven't sufficiently or satisfyingly solved how to calculate. If you can please put up the mass fraction, like the funky exponent.
Oh yeah, right at the end.
Yeah. So if you look at the mass fraction, this 0.02 times sigma to the 13 halves, yeah. So this comes from considerations of how spherical is the collapse, yeah, because you have to have this collapsing spherically or sufficiently spherical, because if it collapses in one direction more than in another, then you get a pancake, or if you have it collapsing in two directions further, you get a cigar. But you need a point singularity, and so this is a power of 5 that goes into there, and the other 3 halves are considerations of if you collapse beyond the Schwarzschild radius before you form caustics that blow things apart again. So this is very
so
uncertain.
they are sort of plausibility arguments.
Yeah, they're plausible.
really
Yeah, of course,
mechanisms.
because you can't do anything better at the moment.
Plausibility arguments.
Yeah. So this is what the Russians came up with 45 years ago. and this is still state of the art. This is how
I think people have only just begun thinking about
Yeah,
this in enough
exactly.
detail to.
Yeah. Except for Bernard, nobody has really done this in the last 30 years. Until recently.
Well, I wonder if there is enough motivation. One of the motivations for these primordial black holes was that people said that actually you couldn't form as the normal end stages of the stars. But actually you can, isn't that so? There's no problem. The issue is that also the formation of black holes in the stars and so on, it has a lot of modeling, and it seems to be that you can produce different results according to what you want to produce.
So an
The same
astronomer is
thing-
probably
the
the
same
best
thing for
person
neutron
to.
stars, the amount of neutron stars mergers, something like that. I don't know. Yes,
Yeah.
here and there.
Well, I can just make a comment on that, because we've written a paper on this recently, like,
By
I-
the way,
I don't-
everybody, this is James Bullock. This is our
Hi,
other
you'll see me
lecturer
later.
of the day.
so that, I mean, I think the current status is you don't have to do anything weird at all to produce the LIGO results. Like, it's
With normal stars.
with normal everything. Like, you just take we know how many low mass stars there are, we know how many high mass stars there are, we know what the metallicity distributions of stars are. I mean, all this stuff is basically empirically determined. If you take just standard models of stellar evolution, it's easy to produce 30 solar mass black holes. Like, it's not, like the Milky Way should have millions of 30 solar mass black holes, just standard. So there's nothing weird about it.
Before it was not done because people haven't seen it.
The thing you don't, yeah, I mean, the thing is, prior to LIGO, you never directly detected them. So what you had seen was like, the biggest black holes that were known were maybe, I think, 8 solar masses or something like that. And that's just because they are pretty rare and they need to be in a binary. You know, it's not easy to detect them. But nobody thought that they weren't there. The real trick is how long did, you know, when you have a binary star system and you've got a couple of really massive black holes that form, do they survive stellar evolution? How long does it take for them to merge? So that's the astrophysical question. But the mere existence of 30 solar mass black holes is not weird. Like, that's what you would think.
So it's not needed to be primordial.
And in fact, the neutron star mergers that we've seen, like everything, even the ratio of the mass of how often you see these different masses merging, it's pretty normal. So it's like, it's not to say they can't be primordial black holes, but like I wouldn't go out and say, oh, there's this huge crisis that we have to build models to create 30 solar mass primordial black holes.
So this was. Any other questions? Yes.
So I have some maybe trivial questions. You are discussing the possibility of primordial black holes as part of dark matter. Is it possible for astrophysical black holes be a significant part of dark matter?
So the question is it possible for astrophysical black holes to be a significant part of the dark matter? And that's actually a good question, because the answer is somewhat subtle if you haven't thought about it before. And it's actually the nucleosynthesis constraints that get you into trouble here. So for instance, back in about 2000, when the Macho collaboration was seeing lots of microlensing events due to sort of half solar mass objects, people were thinking about that then. And the problem is you have to form astrophysical black holes from bigger stars first, and there simply aren't enough baryons in the universe for them to then form a population of stars that then collapse to form black holes that can be a significant amount of the dark matter. So it's because astrophysical black holes would have been formed from baryonic material is the problem here. Does that?
So is there any estimation of like how many primordial black holes in the Milky Way, and what are their masses, and
So there's no concrete evidence that there are. My second lecture will be talking in great detail about all the various ways that you might be able to detect primordial black holes, for instance, gravitational lensing, their dynamical effects, etc. So hold that question to the second lecture.
So all the black holes that have been observed, well, no, actually the ones, so there are different type of black holes, but all the ones that we know of are either the end result of the life of a very, very massive star. Very massive stars at the end of their life form black holes, and these are stellar black holes. All the ones supermassive in the center of the galaxies, we really do not know how exactly they are formed, but those are the ones that are, believably of astrophysical origin. But we don't know. We don't know if primordial black holes exist. All the black holes. But still, for example, the ones that I'm not sure. Maybe James knows more. But the supermassive ones that we have, for example, we have one which is not supermassive, but it is a few million solar masses in the center of our galaxy. But there are AGNs that are huge with respect to that. We do not really know how these absolutely huge black holes form and very early. Maybe you want to comment.
Yeah, I mean, it's a standard problem. How do you go from 100 solar mass seed? So they're like the biggest ones you know how to make from stars. How do you start with something like that and then produce a billion solar mass black hole powering an AGN at redshift, 5? That's hard.
Very early. It's very early and very massive, and it's not clear how they form. So there is a sort of a mystery there. So it's not entirely clear, but those are the ones that have been observed, either those that are the end life of stars, or these very supermassive ones that are the engine of extremely powerful sources in the universe, which still is not completely known. But primordial, who knows?
I have to disagree with that. So if you have a black hole, how can you tell if it's primordial or the result of a collapsing star?
That is true, but actually it is compatible between the end. So it's compatible with the end. So we see them where the stars are.
Yeah, but
So far.
Inherently you can't say it's from a stellar remnant or from a primordial perturbation collapse.
That is true. The ones that have been observed are compatible between the end life stage of massive stars. But of course, if LIGO observes them, for example, once LIGO collects a very high statistics that they will, if they continue finding them, and if they would have the distribution of dark matter instead of visible matter, then you would end up.
I don't know about the details, but I think the spins of the binaries would be one of the ways for testing the origin of them.
The spin too?
Yeah.
Why? They would.
As in you get different spin distributions formed from astrophysical binaries versus primordial ones.
I see. Yeah.
Keep in mind that the problem or potential problem that James just talked about, which is that we know there are billion solar mass holes less than 1 billion years after the Bang. And so how do you make those? Well, the hypothesis is you're building them up from mergers. So LIGO is not going to go after that. For that, we need space-based interferometers that can look at lower frequencies and look for the mergers of higher mass holes.
Yeah, so this is not going to be, but for example, what he's saying is true. And actually, how do you know that even the ones we have observed, are all distributed as where the stars are. But of course, those are the ones that you would see.
So you mean like spatially where the stars are?
Yeah, especially where the stars are. Exactly.
Well, this is also where the dark matter happens to be, right?
No, there is a lot of dark matter where you don't have any stars. The dark matter is distributed differently.
Yeah, okay.
So there are many places in which you are supposed to have a lot of dark matter and you don't have stars. It's distributed differently. I don't know, maybe James wants to.
That's a good point. I mean, you could eventually imagine when you have all these multiple gravitational wave detectors, you could begin to triangulate them on the sky, and you start to correlate. Are you seeing these mergers primarily in big, massive galaxies where all the stars are? Are you just seeing them out in the middle of nowhere with no cross-correlation signal? That would be an interesting, maybe, way to look for that. I haven't thought about that.
Any other question? Okay, then let us go to the coffee break and hope